If we generalize our picture of two-dimensional arrays, that means we're going to have some type, but we'll just stick with int for the moment and generalize the dimensions of the array. So an integer array that is n by m by n, is going to look like this in memory. We're going to consecutively have a0, 0 through a0 n minus 1, and then it will wrap around. So memory goes off the right end here and picks up over here on the left end, and that's where we'll have a1, 0, right? Because this whole top line corresponds to the a0 subarray, which is just a one-dimensional array. This whole line corresponds to the a1 subarray, and so on. So if instead of drawing it two-dimensionally like this, we draw, stick with our linear view of memory, that means the linear view has m times n integers. And the first one is a0, 0, the next one's a0, 1, all the way up to a0 n minus 1. And then, sort of when you would increment to n, you carry the 1 over here and reset to 0. You get to a1, 0. In other words, C uses a row major order. It's called row major because we think of these rows, we have the rows all together, and then columns are spread out across those rows. Or another way to describe it is this is row and column, and the row is a bigger place value than the n here. So this one increments. As this one increments, you step through memory, and as this one increments, you take big jumps through memory. If we perform an array operation, aij, and let's say set that to 17, that is equivalent to getting the pointer that corresponds to ai, and then doing the same thing that we did with the pointer arithmetic to get j. But if we think of it as directly arithmetic on the address a, then it's the same as taking I times n plus j. Right? It's I being the row value times n, because that's how wide our table is. That is the number of elements in this each subarray. Right? So I times n plus j is getting set to 17. These two bits of code are equivalent to each other. So we take this first number times the range of values for the second number.